Can you hear me well?
Yeah, I can hear you better now. My volume is stuff.
No problem. How are you?
Oh, not too bad, honestly.
I'm gonna have to apologize straight away. One of my students was late to their class.
Yeah, man, there's no problems.
So it's a trickle down effect.
Yeah, that's fine.
All right. Without further ado, what do you want to do? What were we up to last time?
Last time we finished projectile, and I did those questions at the end. What am I going through them?
All right, no problem. Let's go through them together.
Yeah, just grab the paper. Somewhere here. Here it is. And also, once we finish this, can we do circular motion? Sweet. Alright. What is this? How's uni going?
Yeah, it's all right. Today was my this week was my week off, and then I have my exams next week.
Okay. You got on a W, yeah?
Yep.
Oh, that's all right. I got the paper. Concept check.
Yep.
1.6.
Mm-hmm.
Yeah. Can I read you out the answer I got and let me know what you got?
Yeah.
All right. So for question 1, maximum height 3.65.
Yep.
Yeah. For B, magnitude of the velocity minus 24.75. Nah, that one was pretty hard. And then
it's just minus 20.
Oh, minus 20. Okay.
It's a trick. Well, I'll tell you to you qualitatively, not mathematically.
Mhm.
So you remember with a projectile how it was symmetrical on both sides.
Mm-hmm.
Well, that means that the velocity is symmetrical on both sides.
Yeah. So Vy would equal minus U.
Just in the opposite. Yeah.
Yeah. Yeah, I kind of stuffed that. I was looking after, but disaster. I'll re-enter that later on. And for C, I got 31.3.
Yeah.
Then we got up to question 2. 9.47.
I'm gonna have to quickly check that one.
Yeah.
Initial velocity, I got 20.
20. Okay, I definitely stuffed something then.
Would you like to go through that question, or do you just want to try it again?
I'll try it again later on. So I'm just going to mark the ones I got wrong. So 1B, question 2 so far. And question 3. Calculate how long time I got 30.6 seconds.
Mm-hmm.
Yep. 3A. Hold on, what was that? Sorry, 3B and 3C. The range 612.24.
I'm just checking B again. Just please give me 1 second.
Yeah.
So what did you say for time?
30.6.
I got 5.5.
Okay. Well, what I got from this, so the change in height's minus 150, yeah?
Mm-hmm.
Yeah, and then UY is 0.
Mm-hmm.
Yeah, and then you go half minus 9.8 times t, and you just divide that across.
T squared.
Oh, it's t squared.
You're to square root it.
Oops.
Yeah. So you have 30.6.
Yeah.
I have 5.5.
5.5. Oops.
Oh.
And then C, that's going to be wrong because I got stuff the time.
Yeah.
Moving on to question 4. What did I get here? Theta equals 82.73.
Yeah, that's good.
Yeah. B, initial velocity equals 197.59.
No.
No. Okay, that's wrong. Question 5. This one is pretty hard, I think. What was the range of values? Where did I write it? 18.43 to 21.28. That's the range of the speed.
Yeah, that's correct. And all you did was use the range formula and just sub in 30 and 40.
Yeah, that took me a while to realize though, but I got it at the end. What was this question 6? What did I log in for question 6? Question 6 was hard. I don't think I got some working out here. I don't think I wrote down an answer though.
Do you want to go through it?
Yeah, question 6. We'll go through question 6.
Okay. Also, I just want to tell you. Wait, hang on. I did something wrong. Oh yeah. All right. We'll go through question 6 right now.
Yeah.
So, can I just? I just did it in my previous class. Can I just send it over my phone?
Yeah, it's fine.
Okay. All right. I'll send them across.
Yeah.
The idea was that the whole stuff about the inclined plane and all that was meant to just throw you off. The idea is that an inclined plane is technically a triangle, isn't it?
Yeah.
So that means that you can abuse. Oh, that's blurry, damn it. So that means that you can abuse right-angled triangles. So you can use trigonometry. You want to tell me what you did?
What I did, I don't know. I started off for the starting angle. I just made it 32. I had
attempt.
Okay, on question 6.
Okay. I'm sending them across. Have you received them?
Sorry, you're cutting out a bit.
Oh, have you received them?
Yeah, I got them now.
Okay.
30 equals 32.
Also, can I ask what you got for 4B?
For 4B.
Yeah.
4B. 197.59.
Okay, I got 205. So yeah.
Yeah. Hold on. Did you just go root 25 squared plus 196 squared?
Oh no, I didn't do that.
What did you do?
So you know how you found theta was 83 degrees?
Yeah.
Did x equals uxt.
Yeah.
So x equals u cos theta t.
Yeah.
So u equals x on cos theta t.
Oops.
So when you did the vy squared, maybe you made an error.
Yeah, probably did. For sure. That's I do the questions at like 11 o'clock at night. Bloody hell. I'm just going to redo all these questions again later on.
So do those solutions make sense for 6?
Yeah, I was looking for it now. It's actually not that crazy. I thought there'd be a lot more working out, but it's all right.
Okay. What about question 7?
Question 7. What did I get for 7? What was the issue?
I can do it on my screen if you want, if you didn't get to do it.
Oh, I got the answer. I got 10.45.
Um,
Or 8.56. I don't know which one it is. Yeah, 10.45 meters per second. Probably got that wrong.
My computer is not cooperating with me. Just give me a second. So what did you say you got again? 10.45?
Yeah.
Yeah, that's correct.
Is that correct? Oh,
Yeah.
beaut.
So that just came from using the kinetic energy formula.
Yeah, I remember that from dynamics.
All right, cool. And then part B is actually pretty simple.
Yeah, I got 1.8.
Yeah.
Yeah.
Oh, no, I got 15.
15.
Oh, no, sorry. Sorry. I'm not having a good day. 1.8, yeah.
Okay, that's fine. 1.8 number 5. Beauty. So the questions I stuffed was 6.
4B.
4B. Yeah, 4B was wrong.
I think 3B. I'm not sure though.
Yes, 3B. The time I forgot to square root it.
Yep.
And then question 2, I think. Maybe 2 wrong.
What did you get for 2? I just want to verify.
UX equals 9.47.
I got UX equals. All right, I'll have to redo that again. Yeah.
Yeah, that's fine. I just you get the time, whatever, and you sub it into the range formula.
Sort of.
I don't know. That's what I did. Yeah. And question 1.
So for 2, I got 20 on the dot.
You got 20 on the dot. Okay.
Yeah.
What did you get for the time?
For the time of flight, I got 2.1.
I got 4.49.
Okay.
I probably did I root that?
Remember, this is type 1 projectile motion, so UY would equal 0.
That's right. Oh, so your total time of flight is 2. What did you say?
2.1.
2.1. Okay.
Do you know how I got that?
Yeah, if you could explain.
Okay. I'll share my screen. It's all to do with subbing it in. So let's draw. So I have x equals u cos theta t. But however, well, this theta is 0, isn't it? So x is just going to equal ut.
Yeah.
Does that make sense?
Yeah.
Okay. And then I also have y. So I have y equals, well, it's just going to be half, well, minus half. Y equals minus half gt squared. All you're going to do is substitute that in. You're going to rearrange for t and sub it into that t.
Hold on, did I stuff up the formula? Is it half gt squared?
Minus half gt squared.
You see, I got t equals 4.49. I just didn't square root it.
Okay. Right.
Yeah, when you're at 4.49, you get 2.1.
Yeah. And then everything else should be fine after that.
Yeah, and then if I sub that in properly, 42.5 over 2.1. I get 20.
Yeah, that's it.
That's So you know what this is, bro? I forgot to square root t for after these questions. That's it. Even for the other one. That's it.
Yeah, but does that make sense?
It makes sense for sure. Yeah, I'm looking at I did the exact same thing. I don't know why I got it wrong.
Okay.
And I didn't square root it.
But are you completely comfortable with substituting things in and whatnot?
Yeah, I'm completely comfortable with that. You know?
I'm very happy with that because that's obviously the harder questions.
Yeah. Well, question 5, once I did that and I got it right, I was pretty happy, you know.
I'm really happy that you got question 7 because no one's gotten question 7 yet.
Oh, really?
Yeah.
Well.
So good job. Pat the back.
Thanks, man.
So before we proceed, I would like to give you a little projectile motion quiz.
Yeah, that's fine.
Okay.
Yeah.
But in the meantime, we'll do it at the end of the lesson because you've just done projectile motion now.
Yeah.
So I'll send you the circular motion stuff and we'll start that.
All right. That's fine. Is it long?
Well, it's going to take about 2 to 3 lessons.
Oh wow, so it's a lot longer than projectile.
Yeah.
Oh, bloody hell.
I'll convert it into a PDF because I've had some complaints about the formatting not working out.
Yeah. That's probably the same thing that happened to me last year. You have to convert it to a Word.
Yeah. So I'll just start. Yeah, people have been actually complaining. They've been like, all right, just relax. All right, cool.
Are you doing face-to-face lessons now?
Yes.
Oh, really?
Yeah.
You have to wear a mask and all that crap or not?
No.
Oh, thank God.
You can come in if you want.
I mean, that'd be a lot better, you know?
All right, no problem. Because this is like I'm not teaching anyone during this time, obviously.
Yeah. Okay. I mean, I'll try to organize my parents. So the new time, what? Usually 5?
Yeah, it should be 5 to 7.
5 to 7. Okay, that's fine.
Yeah.
Yeah. Did you send through the circular motion?
Yeah, it's just loading right now.
Yeah, that's fine. It's probably
All right.
a document.
There you go.
Did you send it in the chat or to my email?
Oh, to your email.
That's
Sorry,
fine.
I didn't specify.
Yeah, that's fine. Yeah, I just got it. I'll print that out.
Is it a little bit better with the PDF?
Yeah, it's all right. It's all right. There it is. All right, I'm just gonna print this out as well. File print 58 pages. Jesus, that's all right. There it is. I put it to print. But we can continue on the PDF while it's printing.
No problem.
Right.
All right. So uniform circular motion. What is it? Well, do you remember what uniform means in physics? It was the first lesson we ever did.
Like constant.
Yeah.
Yeah.
So for regular circular motion, it's just going to be an object going in a circle. But for uniform circular motion, it refers to objects that move in the circle at a constant speed. That make sense?
Yeah.
So this means that it has a constant period as well, because it's going to travel along the circumference every, say, 5 seconds.
Yep.
Okay. So speed is a scalar, yeah? So what about the velocity? Is the velocity the same?
Probably not because it's going in a circle.
Yeah. So because it's going in a circle, that means that the velocity is changing direction.
Mm-hmm.
So that means, and the actual definition is at all instances, so as we can see in the picture, the velocity of the ball is always tangential to the circle.
Yeah.
Have you done calculus?
I've done calculus. Yeah, it started this year calculus. Yep.
But like you know what a tangent is.
Yeah, but just draw a straight line along a curve. Yeah.
Like it touches it once.
Yeah.
Okay. So that comes from the idea that if I were to swing something around in a circle and well, let's say I'm swinging a ball and I cut the string, that ball is always going to fly off at a tangent to the circle, isn't it? By Newton's first law.
Mm-hmm.
So hence the velocity is tangential to the circle.
The velocity is tangential to the circle. Yeah.
Yeah. So it's a tangent to its path.
Mm-hmm.
Okay. So that brings us to our first formula. The first formula is measuring this tangential velocity, and it's going to be the instantaneous velocity, and it's given as 2 pi r on t.
2 pi r on t. So there's velocity at any given point. It's like instantaneous.
Yes.
Okay.
Yeah. And, well, let's think about this. V equals 2 pi r on t, okay? Velocity typically equals distance on time. The circumference of a circle is the distance of the circle, and that's 2 pi r, and the time taken is the same as the period, and that's capital T.
Yeah.
However, let me ask you a question. Would we ever include the direction of this velocity?
The direction of this velocity.
Mm-hmm.
Ooh. Probably not, because it's a circle. You know, it's going in the same, like, you know what I mean? Actually, I'm not sure. That's a good question.
Okay. Well, we've already said that, well, the direction is changing, isn't it?
Yeah.
So how could we pinpoint the direction at any given time?
Yeah. Good point.
So yeah.
Yeah.
But remember, you remember in module 2, or actually module 1, when we spoke about acceleration, and we said that an acceleration is a change in velocity.
Yeah.
Well, technically, when something is rotating, its direction is changing. So that means the velocity is changing.
Yeah.
If the velocity is changing, that means that it's accelerating, isn't it?
Yeah.
So an object moving in circular motion is always going to be accelerating. But the direction of this acceleration is always going to be towards the center of the circle.
Okay.
Does that make sense?
So the object that is going around the circle is always accelerating towards the center.
Yes.
Yes. Okay.
And I can kind of show it to you like visually as well as mathematically. Which one would you like?
Both.
Okay. So visually, if an object is traveling at the same speed, but you increase the radius of the circle,
Yeah.
well, doesn't that mean it's sped up?
If you increase the radius of the circle.
Decrease it.
Or decrease it.
Yeah.
Or yeah, because it's traveling less distance.
Yeah.
Yeah.
Now, mathematically, do you know how to differentiate sines and cosines?
No, I think that's a 3-unit topic.
Okay. You just want to take my word for this?
Yeah, that's fine. I wouldn't mind learning something new.
All right. So, on a circle, so like this one here, we might call this point r cos theta, r sine theta. Pretty stock standard stuff.
Yeah.
Now, if I were to differentiate these, I don't know if you've ever seen this, but this is called the SC tower. SC. And when you differentiate, you go down the tower. So, and also one last thing. Remember that we can like resolve the vectors.
Mm-hmm.
So this vector is going to be pointing out, and this vector is going to be pointing up because the total vector is pointing out of the circle.
Yeah. Okay.
All right, let's switch to red. Remember how velocity is distance over time?
Yes.
That's the same as differentiating it. So velocity is going to equal minus, oh, I should have put a minus there, minus cos theta for x. So I'm just going to put like, maybe I should plan my work. So velocity is going to equal minus sine theta, because by the tower, if I go from C, I go down to minus S, and the y component is going to turn into r cos theta. Now A, if I differentiate again, well, that minus sine theta is going to turn into a minus cos theta, isn't it? By the tower.
If you differentiate, yeah, it was on the tower, yeah.
So we can see that A equals minus R.
A equals minus R. Okay.
Oh, like S, sorry. A equals S. Minus A equals S.
Yeah. Okay.
Yeah. So what does that mean in vector? Well, minus r sine theta is going to be pointing this way, and minus cos theta is going to be pointing that way, and minus sine theta is going to be pointing this way. So doesn't that mean that, well, the resultant is going to be pointing towards the center of the circle?
Ah, so that's how you prove that it's accelerating towards the thing.
Yeah, that's how you actually prove it, but you could just talk about when you shrink the radius, what happens.
Yeah. Okay.
Does that make sense?
Well, it's actually pretty interesting, honestly.
Okay. Yeah. So like for me, learning this in math was just like, what are the applications? But that's why I went into physics, where you can actually see real world applications of what happens.
Yeah. Okay.
So do you have any questions about that? Because I know that's a little bit beyond what you're currently doing.
No, it's fine because it's pretty like you make sense. You've got sine theta, cos theta, and when you differentiate it according to the tower over here, you go down, and you get the answer at the end. It's all right.
All right, no problem.
Right.
All right, so let's kind of move on. So, okay, so if you have an acceleration, that means that we're going to have a force as well, doesn't it?
Yeah.
Yeah, because F equals ma.
Yeah.
So this acceleration that we were just talking about is called the centripetal acceleration, and the force is going to be called the associated centripetal force. But don't worry, there's an actual header for this later on.
Mm-hmm.
Do you have any questions so far?
No. So this centripetal force, whatever, is that the one? That's the one. It accelerates towards the center. That's pretty much.
So that's the force pointing towards the center.
Yeah. Okay.
Yeah. So we have to go over angular velocity. So just like we can have tangential velocity, which is the velocity, you know, like at the edge of the circle, we can also measure the change in angle over the change in time. And that can tell us how fast the object's going as well. So initially we have the angular displacement, and the angular displacement is defined as the angle at which an object moves across a circular path. It is given, so theta equals S on R, where S is the actual distance and R is the radius.
S is the distance and R is the radius. And sorry, what does that give you?
The angle traveled.
Oh, okay.
Yeah. But one thing very important to note, it will never give you the angle in degrees. It's going to give it to you in radians.
How do I convert it from radians to degrees?
To convert degrees into radians, you times by pi on 180.
degrees to radians.
Yep. And to convert radians to degrees, you times by 180 divided by pi.
Let's write that down.
So in physics, it's actually more correct to write it in radians.
Oh, because it's more like exact.
Yeah.
Yeah. Okay. So degrees to radians. I go pi and 180.
Yeah, times by pi on 180. Yeah, and pi is 3.1415, so on and so forth.
Yeah. Okay. And then if I want to go radians to degrees,
Times by 180 on pi.
times by 180 on pi. Okay.
So it's just flip it.
Flip it. Okay. Oh, that makes sense.
Yeah. Any questions about that?
No, that's it.
All right, cool. So very similarly to how we calculated velocity as being the change in displacement over the change in time, we can do the exact same thing for angular velocity. So angular velocity is going to equal the change in the angle over the change in time.
Change in angle or change. What's angular velocity? How fast it travels that specific angle?
It's how quickly the angle is changing.
How quickly the angle is changing. Okay.
Yeah. So, like for example, if you're in a circle and you travel from one point of the circle to the other point of the circle in 10 seconds, well, you traveled pi degrees in 10 seconds. So you traveled pi on 10. That is your angular velocity.
Yeah. Okay.
But as you can see, so for the next formula, this is where we start bringing back things from module 3. So you remember how the relationship between frequency and period was F equals 1 on T?
Yeah.
Okay. So because there's 2 pi radians in a circle, the angular velocity can become 2 pi, because that's going to be the change in the angle, over the period, how long it takes to complete that. And that is going to be equal to 2 pi times F.
2 pi times F.
Yeah.
Okay.
Oh, and just a heads up, the only formulas that will be on your formula sheet are the ones in the dot point on the previous page.
The dot point on the previous page. Oh,
Yeah.
those. Yeah. Oh, so all of these ones need to be memorized.
Yeah.
That's fine. That is fine. Angular displacement, the arc on the radius, that makes sense. Angular velocity, change in the angle over time, that makes sense. And this frequency, yeah, okay, all good.
All right, cool. So this finally brings us to centripetal force and centripetal acceleration. So we've already established that an object in circular motion is constantly accelerating. Why is it constantly accelerating?
Why is it constantly accelerating? I'm not sure.
Well, what happens to the velocity?
Oh, it increases if it's accelerating.
No. The velocity has to change, but you remember how the distance continually changes?
Yeah.
So doesn't that mean that our velocity is changing?
Yeah.
So are we accelerating?
Yes.
Okay. Does that make sense?
Yeah.
All right, tell me that in your own words.
Okay, so you're forever accelerating because how do I explain this? Because your direction is constantly changing. You're on a circle, so you don't have like a linear distance, right? Yeah. So if that is always changing, that means you're also accelerating. Like, I don't know how to explain it.
Because your direction is changing, your velocity is changing, so you're accelerating.
Yeah, that's pretty much it.
All right. And the formula to this acceleration is right there. So we have centripetal acceleration is equal to v squared on r.
Mm-hmm.
So all we're going to do to find the centripetal force is going to use F equals ma. So the centripetal force is equal to mv squared on r.
Okay. Okay. Give me a sec. Let me just go grab the papers from the printer.
No problem.
Oh, I'm back.
Alright, cool.
Let's rip out a highlighter. Pen. All right. Where were we? Centrifugal force and acceleration. Okay. Right. So because your direction is always changing, because you're on a circle, your velocity is always changing, and therefore you're always accelerating.
Mm-hmm.
That's pretty much okay. That's fine. And what was this AC formula again?
V squared on R.
Yeah. And that's just to find that acceleration.
Yeah.
Yeah. Okay. V squared on R. Would the questions give me the radius and the velocity, or would I have to find both of them?
No, you would always have one or the other.
One or the other. All right. And then to find the actual force, mass, velocity squared, mass. Hold on. Mass of what? The actual thing that's being like the object, or
The mass of the object itself.
okay. Okay, mv squared on R. Okay. Okay. All right. So what do we want to do now?
Yeah. So essentially, there's a concept check for you on the next page.
Oh, there's two. Yeah, there's an object speed, velocity, and acceleration when there's a uniform. Okay. Let's see. Well, speed would be constant.
Mm-hmm.
Velocity would also be constant. Yeah, velocity would. Wait, no, because its direction is changing. Yeah.
Yep.
Acceleration. It's well, the object is accelerating. Like, I don't know how to explain it. Could you give me like a proper definition to this answer, like a sample answer?
All right, no problem. So when an object is in uniform circular motion, its speed is constant. However, the direction of this speed is continually changing. Hence, the velocity is changing.
But the direction.
As the velocity is continually changing, this means that we have an acceleration.
Yeah, okay, so speed is constant, but the direction is always changing, making velocity.
Our acceleration is constant as well.
Acceleration is constant. Okay.
Look at the formula, v squared on r. If v doesn't change and r doesn't change, that means acceleration won't change.
Yeah. Makes sense. Right. Making velocity change, therefore acceleration occurs. All right. And that's all because a constantly changing velocity means there's acceleration.
Yep.
Yeah.
But that acceleration is constant.
But that acceleration is constant. Okay. Okay. Using Newton's first law, postulate what a tennis ball is passed to walk up through a uniform circular motion of a rope and the rope suddenly breaks. So, what does postulate mean? Like, hypothesize?
Yeah, just say what you think.
Okay. So, if a tennis ball was swinging in a circular path and you were in the string with the break, at the moment the string broke, the direction of the velocity, like what its final direction of velocity was, the tennis ball would go that way. Yeah.
Yep. But what do you think? What direction will it go?
Well, in whatever direction. Oh, that's a good question.
Okay, let's say the ball is traveling clockwise.
Clockwise. Yeah.
Yeah. And it's at the top.
At the top, traveling clockwise.
Yeah. So like you can draw a circle and the ball's here traveling clockwise to your right.
Tomorrow. Yeah.
If the rope snaps, where would the ball go?
The ball would go bottom right. South. Wait, no. I don't know.
Well, by Newton's first law, can you tell me what Newton's first law is?
That one's the inertia one, isn't it?
Yes.
An object that is in motion will stay in motion unless there is an unbalanced force acting upon it, I think.
Yeah. So if the string suddenly breaks, is there any force acting on the object in circular motion?
No. Wait. If the string breaks, that means that. Wait, I don't know. I'm confused.
If the string breaks, so we're ignoring gravity and stuff like that here. If the string breaks, there's no longer any centripetal force acting on the ball.
Yeah.
Because it won't be traveling in a circle anymore.
Mm-hmm.
So by Newton's first law, it's going to remain in constant motion, isn't it?
Yeah.
So if it remains in constant motion, what way is it going to travel?
Well, it remains in constant motion, and we're still going in a circle if it's going in constant motion.
No, it's going to travel off at a tangent to the circle.
The tangent to the circle.
Yeah. Do you understand why?
No. Hold on. So the string breaks, and there's no more force pulling it in.
No.
Right? So. No. Could you explain it further?
Okay, so if we go back to the very first page, you remember how the velocity is tangential to the circle?
Yeah.
So if the string is snapped, won't the ball follow the direction of the velocity?
Yeah.
So it will travel tangential to the circle.
Yeah. Oh, yeah, that's right.
Are you satisfied with that?
I'm actually pretty satisfied. That was a that was so simple. I don't know why I ever thought that.
So good.
Tangential. That's a good word to remember. Tangential. Tangential to the final velocity.
No, the velocity is tangential to the circle. It will travel off in the direction of the tangential velocity.
Yeah, okay. Right. A 900 kilogram car is moving at 10 meters per second and takes a turn around the circle for a radius of 25. 10 of the acceleration and the net force acting upon the car. Right. What are my formulas? AC equals V squared on R. FC equals mv squared on R. Right. Acceleration, velocity, 10 squared, 25. This is pretty much subbing it in question 3.
Yeah.
So,
yeah. You can skip questions 4 and 5, but I do want you to do question 6.
so 3, 4, 5, they're all like whatever, subbing it in, yeah?
Yeah. You can do those for homework if you want, but I definitely want you to do question 6.
Yeah, 3, 4, 5, whatever. Okay, question 6. During the spin cycle of a washing machine, the clothes stick to the outer layer of the barrel as it spins at a rate as high as 180 revolutions per minute. The radius of the barrel is 26 centimeters. Determine the speed of the clothes in meters per second, which are located on the wall. Okay, so first thing we're going to do is convert centimeters to meters, so 0.26 meters.
Good.
1,800 revolutions per minute. Oh, that makes sense of that one. And how many would be per second? 1,800 divided by 60, that's 30 revolutions a second.
So that's 30 hertz.
30 hertz, yeah?
Mm-hmm. That's your frequency.
That's my frequency, yeah? So now I have the radius and the frequency, determine the speed. Right, what was my formula? What was my formula? AC V squared on R, no. FC and V squared on R. Wait, what? Hold on. I have, there's only two things I'm given. Determine the speed in meters per second. I don't have the acceleration. I have to use the frequency one. 2 pi. Okay, so I know that angular. What's its face? Angular velocity equals 2 pi times 30. 2 times pi times 30. 188.5, whatever. That. Change on pi. So change on. So okay. What would I do here? The only two formulas I have that are V is the FC and the AC. I've rated. How would I find the acceleration here?
You don't have to find acceleration.
I don't have to. Okay.
It's asking for the speed, yeah?
Yeah.
But you're given a radius and a frequency.
Yeah.
How do FC and AC don't involve frequency?
Yeah, so I crossed them two out of my mind. Yeah, but they're the only ones that have speed. That's the thing.
Go back to the first page.
Oh, V equals 2. I didn't see the one. Okay. Because looking, I'm like, what am I supposed to do? There's the only two that have the thing, but there it is. V equals 2 by R T. There it is.
But you don't have T.
Well, doesn't F equal 1 on T?
Perfect.
Yeah. 30 equals 1 on T. 30 T equals 1. T equals 1 on 30. There it is. I didn't even see the formula at the front. 2 times pi times 0.26. 1 on 30. 49?
Yep.
All right, perfect. Is that one at the front on my formula sheet?
That first one is, yeah.
Okay, sweet. The most obvious one, I didn't even look at it, man.
You hit alone.
Yeah. V equals 49. Right. Determine the acceleration. Which one has acceleration? That's the V squared. Okay, that's easy. 49 squared on the radius 0.26 A equals 9,234.6. What could have I done?
You asked to find the acceleration, yeah?
Yeah.
So V squared on R.
Yeah. 49 squared on 0.26.
That's what I did.
Yeah.
I got 9,240.
I got 9,234.62.
Oh, okay, yeah. Sorry.
Yeah.
Yeah. Pretty similar. We'll say it's a rounding error.
Yeah, whatever.
Because I kept it exact.
I just rounded it to 49. I'm like, whatever.
I'm
like, what could have I done now, bro?
No, but that's why we use significant figures.
Yeah.
So we would both say it was 9,200.
Mm-hmm. Yeah, if it's significant figures, yeah. Right. That's it. That's it for 6. Is there question 7?
Nah.
There we go. All right. Sweet.
Alright, are you happy with that?
Yeah.
Alright, yeah, you're just gonna have to do the other two for homework.
Yeah.
they're more wordy questions that are a little bit more annoying to deal with.
Mhm.
All right. Did you have any questions, or did you found it pretty straightforward?
So far, it was all right. I just need to get used to the formulas.
Okay.
All right.
All right. So on the next page, we're going to do a mini practical, and you can also see my writing.
Yeah.
So the idea for this is that, well, we're trying to determine the relationships between centripetal force and mass, centripetal force and velocity, centripetal force and radius, so on and so forth. And we can already see what they are through the formula. Do you agree with that?
What formula? The ones previous or?
Fc equals mv squared on r.
Yeah.
We can see that, just like how F equals ma.
Yeah.
F is proportional to m, F is proportional to v squared, F is inversely proportional to 1 on r. So the whole point of this prac is for you to actually come up with these ideas. So for example, you're going to test two things. So I've given 3 tables for this. So we can do this together. So I'll do the graph, and you can just kind of copy it out if you wish. I don't particularly mind. But so initially, let's say that we're going to test R versus M. So that means that R is going to be here and M is going to be here.
All right. It's supposed to be dependent on the left, yeah?
Yes.
Y-axis. Right.
Oh, well, it's always Y versus X in the title.
Yeah. Y versus X. Okay.
Yeah. So by the formula, which is Fc equals mv squared on R, what is the relationship between R and M?
R and M.
Mm.
I don't know. Inversely. Or I don't know.
They're just regularly proportional.
How does that work?
So the idea of the proportional things is that if every other thing is constant, so let's say Fc equals 1 and V squared equals 1, what does M and R equal? Well, so 1 is going to equal to M on R. So therefore, M is R. But however, we can't say M is R because we've already set the other things to 1. So that's why we say R is proportional to M.
Okay.
Does that make sense?
Yeah.
Okay.
So as it increases, mass is supposed to increase.
Yeah. So what will be my graph? Will it be a straight line or a hyperbola?
Or straight line?
Yeah, because as one increases, the other increases.
Yeah.
Cool. So you're going to get a straight line like that. And the question that you're going to be asked, or you might actually be assessed on this, because I was assessed on this in my first task in year 12.
Mm-hmm.
What you are asked is, well, find what FC is. So what you would do, the radius, not the radius, the gradient, so I'm just going to do capital G, is equal to R on M, isn't it?
Yes. Rise over run.
But by the formula, this is equal to Fc on V squared, isn't it?
FC on V squared.
Because I just divided this V squared over.
Yeah, like when you arrange it, yeah.
Yeah. So that means that to find the centripetal force, Fc is going to equal the gradient times V squared.
Mm-hmm.
And that's how you find centripetal force.
That's actually all right.
Yeah.
Right.
And you can find the velocity through measuring the time it takes to travel the set radius.
Mm-hmm.
Because you already know what R is, so you can do 2 pi R, and you just got to measure the period T.
Yeah.
Any questions about that one?
Nope.
Do you want me to just stay on here for a couple of seconds so you can write it down, or do you already have it?
I don't write it down, but because I'm looking, You wrote that as proportional. I'll just write the G swing. I mean, you're already recording the lesson, yeah?
Mhm.
Yeah. Right. It's fine.
Okay, so for the second one, we're going to do, well, another one, obviously. And just give me a random one.
We're doing random one. Like,
Give me 2 random things to draw a graph with, and I'll do it and show you.
I don't know, V and R.
Okay, so it's going to be v squared versus r.
Yeah, V squared plus R. Okay.
All right, so by the formula, FC equals mv squared on r. So that means that if I were to put everything to 1, v squared would equal r. So that means that v squared is proportional to r. Did you see that line of logic?
Mm-hmm.
Okay, so I'll get a straight line. So that means that the gradient g is going to equal v squared on r, which is going to equal fc on m. So therefore, fc is equal to m times the gradient.
Okay.
Does that make sense?
Yeah, that makes sense.
All right. So we'll do one more. I'll give this one to you, and you can tell me the logic behind it.
Right.
So let's say I already know what the centripetal force is. I've measured it in newtons somehow.
Yeah.
And I measured the radius of the object.
Yeah.
How would I find the mass? So you just tell me and I'll draw it.
You have FC and you have R.
Yep.
You're missing V and you're missing M.
Mm-hmm. But I'm trying to find m.
You're trying to find M.
Yeah.
The formula is FC equals mv squared on R. Trying to find R. You go FC times R on V squared to find M.
But like in terms of the graph.
In terms of the graph,
Yeah.
um,
Are they directly proportional or inversely proportional?
the force and the radius,
Yeah.
isn't it inversely proportional?
Yeah. Why?
Because remember what we said last time, if you shorten the distance, you have a lower acceleration.
Perfect.
Yeah, that's why. And this one would be a hyperbola, yeah.
Yeah. But do you remember the trick that we had if something was inversely proportional?
Put a 1 over that thing. Is that
Yeah.
the thing?
So
Yeah.
it turns into V verse. So F verse 1 on R. So we get the straight line.
Yeah.
So that means that the gradient is actually going to be, so G is actually going to equal FCR. Because the denominator of the denominator becomes the numerator.
Yep.
So tell me what I have to do to get M.
To get M, right? FCR. To get M, we have mv squared. You divide the gradient by v squared.
Perfect. And that's it.
Yeah, and you get M. That's right. Perfect.
That's simple.
Yeah, it's not even that hard. Is this supposed to be like a practical? Like, could they give me an
Yeah,
example?
this is an actual crack. So if I go up, yeah. So if I go up, this is the actual dot point. It conducts investigations.
Yeah. They've got to give me something similar to this in the exam.
Yeah, well, this is what I did. This is what I actually submitted for my assignment.
Yeah. Okay. Well, that's actually not too bad then. I thought.
Yeah. So you don't have to do question 1, but I would like you to talk to me about question 2.
Question 2. Okay. Uniform centripetal force, speed, mass, and radius. Okay. So I can straight away tell you if the radius decreases, the centripetal force decreases.
Okay.
Therefore, the speed also decreases because the acceleration has decreased.
Okay.
Yeah.
Just a question.
Yeah.
We determine the relationships by setting all of the things equal to 1.
Mm-hmm.
If the velocity is changing, oh wait, hang on. Oh no, so question three. We already did question 2 together.
Yeah, question.
Sorry.
Okay. Yeah, okay. What would happen to what proposal would happen to the relationship for not okay, so now it's not constantly accelerating.
Yeah.
Okay. Okay. Well, I'd say centripetal force would increase. No. Hold on. Why wouldn't it increase?
Well, it's not that it wouldn't increase, it's that all the relationships fall apart.
Why?
Because we can only determine if something is proportional to something else if we keep everything else constant, so we ignore them.
Yeah, okay.
But if v is changing, then because it's not in uniform circular motion, then how can f be inversely proportional to r?
You can't. Oh, I see what you mean. You can't be because if it's not constant. It can't be. Yeah. Okay.
Yeah, because like let's say I'm decreasing the radius, so that would increase the force, wouldn't it?
If you decrease the radius, that would decrease the well.
Increase the force.
It increases the force. Okay.
Yeah, because they're inversely proportional.
Yeah. Okay. Sorry. Yeah.
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 What happens if I decrease the radius whilst increasing the speed?
Decreasing the radius. I need to look back at the relationships.
Everyone?
You decrease the radius, but you increase the speed. Is that what you said?
Yeah.
You decrease. So it's being faster around a smaller circle.
Yeah. Well, what I'm trying to say is r is only, it's not squared, is it? But the v is squared. So that means if v is increasing, but r is decreasing, doesn't that mean that my centripetal acceleration could get even higher and higher?
We're looking at the formula, yeah. If you have a smaller denominator.
Yeah, so it's not going to be a straight line.
Yeah. I need more of exponential.
Yeah.
Yeah.
But like, let's take the other example. Let's say my velocity is decreasing whilst my radius decreases.
Your radius what? Increases?
The radius decreases,
Yeah.
but so does the velocity.
Okay, so your smaller circle at a slower speed. What would happen to the force?
Yeah. Well, the force might actually go down.
I'm gonna look back at the relationships again. Smaller radius and smaller. Yeah, so the overall, if everything drops, the thing will drop as well.
Yeah.
Because you're decreasing the denominator and the numerator. You'd have a smaller thing overall. Yeah.
Yeah.
Okay. Well, that's an important formula.
Yeah.
Could they only give me questions in the practical just about that formula? Like about the force?
This whole prac is about the formula.
Yeah, that's what I'm saying, but could they give me a different prac that's not about the centripetal force? No?
No, it's the only prac with centripetal force.
Yeah, okay, sweet. Sweet. Right. So far what I gathered from all this, right? From the prac, right? It gives you all the relationships, yeah? So centripetal force changes with mass, velocity, and the radius, yeah?
Yep.
And then we have all the relations between each of those. Okay. I just need to memorize the relationship between each of those, pretty much. Yeah, okay. That's fine. That is fine. Okay. That's it. Want to move on?
Yep.
Yep. Okay.
So now that we've kind of looked at what the formula is and all that stuff, we can now actually look at the applications of uniform circular motion.
Mm-hmm.
So, well, what is this? These are real-world examples of how circular motion can occur. So the things that we're going to be looking at are the subdot points. So a car moving around horizontal circular bends, a mass on a string, and objects on bank tracks. And this will probably be the last thing we do today because we're going to do the projectile motion quiz later.
Oh yeah. Okay.
Yeah, and this is pretty massive. So like, yeah, your math game has to be on.
Yeah. Okay.
All right, cool. So the first one is a car moving around a uniform a horizontal circular bend. So I'm going to be referring to these images on the right-hand side to justify my points. So say the car is going around the circular part between B and D.
Yeah.
Because it's a circle, the car's going to be technically experiencing a centripetal force, isn't it?
Yeah, because it's going around the circle. Yeah.
Yeah, but if you look below that little the road image, you can see a force diagram acting on the car.
Yeah.
Well, if we look at the forces vertically, we can see the normal force and we can see the weight force, and they're going to cancel each other out.
Yeah.
Now, the only other force that can actually be a part of this is friction.
Mm-hmm.
And friction is going to be pointing in the opposite direction to the car, isn't it?
Yeah.
So because the car's going in a circle, the friction is going to be pointing towards the center.
Towards the center of the circle.
Yeah, so it's a little bit different to normal friction. Like, it's not straight.
Yeah. Hold on,
So-
let me gather that for a second. So if your car's going around the bend, the friction force is going to be pointing towards the center of the circle.
Yeah.
Okay.
And, well, the friction is the only force pointing towards the center. So that means that the centripetal force is the friction force.
The centripetal force is the friction force. Okay.
Does that make sense?
Yeah, because on the last thing we were talking about the string, which is a centripetal force pointing towards the center. Now it's the friction. Yep.
Yeah.
Okay.
All right. The second thing is a mass on a string. So the first one is if I just swing something around like this.
Mm-hmm.
Now, if you look at the diagram on the right, if we have a mass on a string, we have a tension force, don't we?
Yeah. Is this page 13? Yeah,
Yes.
here it is. Yep.
Yeah. So if we have a mass on a string, that string has a tension force in it.
Yeah.
And that tension, well, remember the definition of tension? It always points away from the mass.
Yeah.
Well, that means that the tension is pointing towards the center.
Ah, so that's also another centripetal force. Yeah.
Yeah, so the tension in this case is the centripetal force.
Yeah, I see.
Yeah. And that happens once again because, well, all the other forces kind of cancel each other out.
Sorry, you were cutting out.
Oh, and this happens because just like with the car on a circular bend, all the other forces kind of cancel each other
Yeah. Okay.
out. Yeah. But I like to point out again, just like how we looked at the question earlier, if the rope were to break, the ball would fly off at a tangent to the circular path by Newton's first law.
Mm-hmm. So
Just
if
like
I just point that black circle, it would go along V.
yeah.
Yeah, I see.
All right. Now, that's pretty straightforward, just a regular mass on the string. But there's a further application of the mass on the string that makes things pretty difficult.
Mm-hmm.
And this is the conical pendulum.
It looks pretty difficult. Yeah.
So the conical pendulum is essentially just like a mass on a string, but it's hanging from a ceiling.
Yeah.
So it creates a cone.
Mm-hmm.
Okay. And because it creates a cone, different forces that are acting on here. So one thing I like to point out is that this image has made a mistake. Instead of F, it should be T.
Tension.
Yeah.
I'll change that real quick. T. Yep.
All right, cool. So what we're going to do, we're actually asked by these dot points to derive equations that describe several things. So on the next page, I'm going to ask you to equate the forces horizontally and vertically for the tension. So find the tension force horizontally and find the tension force vertically.
For the pendulum.
Yes, for the ball.
Yeah. Okay. So vertically.
And rearrange for T on both of them.
Yeah. Well, vertically is just wait. Hold on. Is the vertical one supposed to cancel out?
Well, sorry, did you say they cancel out?
Do they cancel out?
No, they're equal to each other. So one's up, one's downwards.
Yeah, okay, so yeah, that's fine.
So what do you get for the vertical?
Well, for the vertical, I'll just put weight force equals T cos theta.
Yep.
Yeah.
And what about horizontally?
No, that's right. Weight force equals T cos theta, and then horizontally, T sine theta. Yeah, is it just T sine theta?
But it's in circular motion.
That's good. Oh, the angular thing. Okay, I've got no idea for horizontally then.
T sine theta is going to equal mv squared on r.
Hold on, you're cutting out again.
T sine theta equals mv squared on r.
T sine theta equals.
Because it's towards the center.
Oh, yeah, because that is the centrifugal force. Yep.
Yeah.
So
they are two expressions.
Yeah.
Now that you have those expressions, I want you to derive an expression for the velocity, so make velocity the subject, in terms of g, tan, and r.
Yeah, so T sine theta equals mv squared. Yeah, that's the formula. Mv squared on r. Okay. For velocity in terms of g, tan, and r. Okay, so I get that. I don't understand g and tan theta, where they come from.
Well, you're meant to combine the two equations.
I suppose combine them. Oh, okay.
Yeah. So, like for example, T cos theta equals mg, and T sine theta equals mv squared on r. There's your g.
T cos theta equals weight. T sine theta equals mv squared on r.
And you have to combine the two.
How am I supposed to combine T cos theta and T sine theta?
Oh, okay. Make T the subject.
So pull out T out of the equation, and then you put weight on cos theta. Ah, there it is. Sorry, mate.
And then sub it in.
Oopsie doopsie. Can't believe I didn't see that. Okay. Work on cos theta equals times sine theta. Ah, there it is. Times sine theta equals mv squared on r. And then sine on cos is tan. Then we have weight force, which is g tan theta equals mv squared on r. G tan theta times r equals mv squared.
The m's will cancel.
R?
The m's will cancel.
G tan theta times r. M squared. So it's a square root g tan theta times r on m.
Yeah, so v equals root gr tan theta.
GR tan theta on M.
No, m's cancelled.
Okay. So just root G tan theta times R.
Yes.
Okay.
Yeah, so V equals the square root of GR tan theta.
Yeah, that's right.
Perfect.
Perfect. Okay.
That's it.
That's all right. Silent theta work. Yeah. Okay. Beautiful. Beautiful. All right. So what do we do now?
Just give me a second. So now that you have that, that's essentially, well, there's a concept check later on that is going to answer the whole dot point. But the next concept is actually an application of banked tracks. But the next thing is called banked tracks, and it is an application of inclined planes.
Bank tracks.
Yeah, that's what it's called, the next thing.
Yeah. Okay.
But they're essentially inclined planes. Do you remember how to do inclined planes?
Yeah, I think I remember a fair bit.
All right. I won't go over the theory, but do you want to do 2 questions for me?
On inclined planes?
Yes, please.
Yeah. Okay.
Can you do questions 10? Oh no, actually 10 and 11 are pretty similar. Do question 9 and question 11.
Question: the 100-kilogram box?
Yep.
Yeah. Okay. Let's see this. 100-kilogram box is lowered at a constant speed down, so constant speed, no acceleration, down an inclined plane 4 meters long from the back of a lorry 2 meters above the ground. Okay. The coefficient of friction, so mu equals 0.45. What is the magnitude of the force F to be applied parallel to the inclined plane to hold the box? What is the magnitude of the force F to be applied parallel to the inclined plane? Okay. And lowered at a constant speed. So mg sine theta. Okay, hold on. Let's do this. mg sine theta and the friction force are supposed to be on the parallel thing, yeah? Yeah, okay. What is the magnitude of the force F? Okay. Give me a second. Sorry, I'm back.
Okay.
Right. So, it's not stationary, it's being lowered. Okay.
However, so this is a real flashback, but it says that the box is going to be lowered at a constant speed. That's a very big hint.
Yeah, so there's no acceleration.
Yeah, so that means your net force is equal to 0.
Yeah. So 0. Mg sine theta minus F mu theta equals 0. F. Hold on, what's the formula for friction again? Is it just F mu theta? Mu?
Mu n.
Oh, sorry, the normal force. Sorry.
Okay.
Yeah. So that means N nu equals mg sine theta.
Oh, not quite.
Really?
Remember, if the box is going, if the box is going down the plane, that means that gravity is acting downwards, and what do you call it? Friction is acting upwards, isn't it?
Yeah.
So there's a third force being added. So I'll just kind of draw them for the heck of it. So if the box is here, This is gravity. This is friction. And, well, yeah, it's going to be another force. Say it's going up the slope.
Yeah.
So the force plus the friction force should equal gravity.
Yeah. But what's the other force?
Well, that's what we're trying to find. This is F.
Oh. Hold on. You said it's going down the thing.
Yeah, but well, it's traveling downward, so this is V.
Yeah, that's V. Yeah. F. Okay. What's that? Oh, so we'll just go mg sine theta minus m nu minus F.
Mm-hmm.
Yeah. So just go F equals mg sine theta minus m nu. Do we have the mass? Do we have the gravity? Do we have the theta? Do we have theta? Do we have theta? No. F equals mass 100 minus 9.8 sine theta minus the normal force, which is mg 100 minus 9.8 0.45. Okay. So F equals minus 980 sine theta minus 441. So I got so far.
What did you say your final answer was?
No, so far I got the force equals minus 980 sine theta minus 441.
I just put mine in variable form and then substitute, so I have a final answer.
Oh, you already straight over final answer.
Yeah.
Honestly, bro, I got no idea. We don't have theta, yeah?
Yeah.
Yeah, I don't know what to do.
Okay. You want me to do it?
Yeah, do it.
Alright. So what I did, your net force, so I'll zoom in a little bit. No. My net force is equal to 0. And that is the forces up the slope minus forces down the slope.
Mm-hmm.
But we remember from inclined planes that n equals mg cos theta. Yeah.
Mm-hmm.
All right. So that means that F going to equal mg sine theta.
I don't know what an idiot, bro. I put n equals just mg. Oh my god. All right.
You got to tell me what the angle is.
What the angle is?
Mm.
Oh, so no, that's 90.
I'm trying to find this, yeah.
Yeah.
We know that sine theta is going to equal half, yeah? Opposite on adjacent.
Yeah.
Right.
Right.
So that means that theta is going to equal the inverse sine of half.
Yeah.
But what is the sine of inverse sine?
what is the sine of, so the inverse sine of half is 30. So you just go sine 30.
Perfect. So we know that the angle is 30.
Yeah. Well, that's pretty easy.
And then that's going to be cos 30 as well.
Yeah.
So all I did was factorize out the m and the g because I didn't want to write out it twice.
Yeah.
So sine 30 minus 0.45 cos 30. And that is 108 newtons.
Yeah. Okay. So we know it's constant, so there's no force, the force plus the friction minus mg sine theta. F equals mg sine theta minus nu theta. Yeah, okay.
You good with that?
Yeah, I'm good with that.
Okay. You can do the next one, or would you like just to do your test now?
I'll do the next one actually. It's a good revision.
All right, no problem.
The block in the diagram below is at rest. Okay. However, the tension. Oh no, tension in the cable is not only the thing. Static friction also applying force determine the tension in the rope. Okay. Force acting down. Okay, so mg sine theta equals to T plus M. Okay, so mg sine theta equals the tension force plus the static friction. Yeah. Mass, do we have the mass? We do not have the mass. Actually, we do have the mass, 33.2 sine 31.5 equals T plus M 33.2 G minus 9.8 times this isn't too hard. Divide that across. Wait, minus, sorry.
But are you doing 10 or 11? Just want to double check.
10.
Okay.
Do you want me to do 10?
I was gonna. I thought you were doing 11 at first, but I was like, that sounds like you're doing 10. So I just wanted to double check.
Yeah, 10. I thought you said to do 10.
Oh, good.
Yeah.
You can do 11 for homework if you want.
Yeah, do it for me, sorry. Tension equals 294.76. Right. How much time do we have?
We have half an hour, which is how long your test is.
Oh, perfect. We'll just do that. We will do the test. What's the rest of the stuff? Okay. Perfect. Are you gonna email with me the test, or like, what's gonna happen?
Whatever you want. If you want me to stick.
I mean, send me the test.
I already sent it to you.
I already sent it to me.
Yeah. Give yourself half an hour to do it. Don't be sneaky.
Yeah.
And can you, like, on WhatsApp, send me your solutions?
Yeah. Oh, it's only one page. All right.
Yeah. It's half an hour. It's 20 marks.
I'll print that out. Right. When do we?
Oh, whenever you want. You can do it. You can send it to me right after the lesson or whenever. I think. Yeah.
Can we add this half an hour to next week?
Huh?
Can we add this half an hour to next week?
You're gonna end the lesson here.
Well, I don't know. Up to you.
This is meant to be part of the lesson.
So I meant to do the quiz while you were here. Oh, okay, that's fine.
That's why I asked. You want me to stay with you?
Yeah. Okay. Yeah. All right. Yeah, I'm gonna do the quiz. All right. All right. Let's see this. Question 1.
So every week, so this is gonna be like Sam. You know how Sam does his speed tests.
Yeah.
This is your equivalent of a speed test.
Okay.
Yeah.
That's fine.
So the better you do, the more time I take off for next time.
Yeah. All right.
So I'll set you a half an hour timer if you wish. I can just share my screen for you. All right, tell me when you're ready and I'll start the timer.
I've got paper. Give me a sec. Where did my calculator go? Here it is. Well, now just to make sure, right? The formula is changing y equals uyt plus half ayt squared. Yeah.
Yeah, you can have your formula sheet out in front of you.
Yeah. Okay.
For the first one, not for the next one.
Yeah. That's right. Is that the point? I just want to make sure because now I stuffed those questions about the t squared.
Mm.
Yeah. No. Yeah, so it's clear. Yeah, Zach.
All right. 3, 2, 1, go. So so every lesson you can have a mini test.
Sorry, I'm back. Oh, you started the time. No. Question. A stone is horizontally from the top of a vertical cliff. Again, the initial velocity is U equals 20. And it hits the horizontal ground below. Oi. I just finished question 1.
It's a test.
Oh, okay, right.
But you're gonna have to like admin stuff, but not like, is this right?
Yeah.
Just for curiosity's sake, what
Yeah.
question are you up to at the moment?
4.
Okay, that's really good.
Yeah. Bro, I almost got stuck on 4, and I realized it said vertically upwards, so the angle was 90 degrees.
Yes, exam. I can't tell you it's an exam.
Yeah. Can we go through the answers?
Are you finished?
I didn't do 5. Did the other ones.
You're gonna give up,
I didn't do 5.
but you have 3 minutes left.
Yeah, I don't know how to do 5. I spent a bit of time on it. Don't know how to do it.
So you want to leave it here?
Yeah, Olivia, can you give me the answers?
Yeah, no problem.
Alright.
But I'll give you the answers, but you have to what do you call it? Give me your working.
Yeah, it's fine. I'll send it to you now on WhatsApp. Question 1. Question 2. Question 3. Question 4. I don't know, 5 is a disaster, but I'll send it anyway. Right.
All right. So 1A was 60 meters.
Yeah, I'm just selecting the things.
Okay, no problem.
Right.
All right. 1A was 60. You got that right. So you get 1 out of 1. You can just write this next to your questions in red pen if you wish.
Yeah, 1A is 60. Yeah.
For B, it asked for the height of the cliff, not how far it fell.
Oops. So what's the height?
So you are right. It is 44.1, but you said minus 44.1. So I had to give you a half mark for that.
All right, that's fine.
Yep. And for part C, you got the velocity right, but you didn't give me the angle.
Oops.
The half mark again.
Yeah.
You happy with that?
Yeah, that's fine.
For question 2, oh wait, where's question 2? Oh, here we go. For question 2, time of flight was 2.55, max height was that. Yep, they're all correct.
Yeah.
But I can only give you 1 out of 2 for each of them.
Oh, the units.
No.
What?
You have to derive the equations.
What? But are there?
In the exam, you have to derive max height, time of flight, and things like that.
Are you serious?
Yeah.
I didn't know that.
That's
Okay.
it. Okay, so looks like you're on 2. All right. For question 3, that was what was question 3? Question 3 was the crate of supplies.
Like the range. 4.
Yeah. So why do you have time?
Because I got the time.
Was there another part that I'm missing?
Look to the left.
Oh, okay, yeah, sorry, my bad. Yeah, sorry, I didn't see that. It was 404 meters. Good. Let's see your working. Yeah, I'm happy. 3 out of 3.
Yep.
Good. For question 4, the stone is thrown vertically upwards. What did you get? You got 5 seconds?
Yeah.
The answer was 8 seconds.
8. Okay.
Yeah.
Yeah.
What happened? So you tried to find max height and then the second half.
Mm-hmm. So minus 122.1 equals half AYT squared.
I'll give you 2 out of 3 for that.
I stuff up.
You stuffed up because you just added the 2 distances together without considering that it went up and then went down.
Yeah, I added the change in height to the height of the cliff, 122.1.
Yeah, but that change in height could have been, it was just dropped from that point.
But isn't that the change in height that occurs?
Yeah, but what you had to do, you actually, using your delta y equals 43.65, you had to find the time to get to max height.
Oh, at T1 and T2.
Yeah.
I see.
Yeah.
Oops.
So you only did one thing wrong, so I'll give you 2 out of 3. Yeah, I gave you 2 out of 3.
Okay. Bloody hell. So this is only half of it. So this is only part 2, sorry. So 5 seconds only T2.
Yeah.
Yeah, I see.
And 3 seconds was T1.
Yeah, okay.
And then for question 5, let's see what you have here.
5 I tried it, I just disaster. I don't know what I don't know
So
what
is that all for part A?
Yeah.
Okay, so that was worth 3 marks.
Diagram correct? Like, did I think about the question correctly?
The diagram is correct, and you'll get an actual mark for that.
Okay.
All right. Mark for A for progress, but then I have to give you 0 for 2 for part B.
Yeah, that's fine. I didn't even attempt it. How would you do?
You want to know what you got?
No, I don't know what I want. What would you do for 5?
Oh, okay. So for question 5, it wasn't too tricky.
I don't know. Like, I think I just had a mind blank.
Let me just look over to my work. So for question 5, do you want me to write my solution or just talk about it?
Just talk about it, like, you read off the screen.
Okay, so I had x equals uxt.
Yeah.
But I don't know what v is, what u is.
Yeah.
So I rearranged for t and to y equals uyt plus half ayt squared.
Oh, that's smart. That's very smart.
But you were on the right track. You just didn't substitute t.
Yeah.
So I didn't give you anything but setting up the equations.
Mm-hmm. Okay.
So you got 11 out of 20, which is pretty good.
11 out of 20 are barely a pass. Disaster.
It was your first test and we started last week.
Yeah. It's all right.
So I think that's a win.
A pass is a win. Okay.
Yeah.
Bloody. So I didn't know you had to derive the equations for the exam.
Yeah.
Oh wow. Okay. So that's something I need to know how to do. That's all right.
Do you have any questions?
No. No. 5. Before I realized what I stuffed up, 5 was pretty easy. Yep. My bad. All right. That's pretty much it.
All right, no problem. If you have any questions, let me know.
Yeah, no worries. I'll text you.
Would you like some more projectile motion questions? I can just send a document.
Yeah, send me a document. Why not?
All right. All right. This isn't my document. It's just a document that my teacher gave me when I was in year 12.
Oh, really? Do you have the answers for it?
No, unfortunately. But there is projectile motion calculators online.
Mm-hmm. Oh, really? Is that a thing?
Yeah, just look up projectile motion calculator and it will give you the calculator, and you type in what the question gives you and it'll spit it out.
Ah, okay. I've got to actually check that. That's pretty mad. I don't know about that.
All right, I just sent it to you.
All right, sweet. Thanks, mate.
No problem.
All right. So that's all for this lesson, yeah?
Are you okay to do a test every lesson also?
Yeah, of course. Would really. All right. Oh, we went 10 minutes over time. My bad, man.
I don't particularly mind. It's all good. I get home at the same time anyway.
Yeah. All right, sweet. All right. Anyways, thanks for the time, mate. I'll see you next week.
See you next week. Bye.
Bye bye.